Good evening, sixth form. As promised, I said I'd do a short screencast to go through one of the problem questions. Now this is question 14, and it was a question that many of you struggled with, so I'm going to go through it now. The question asks you to explain this graph here. Okay? Now, you have to explain it, not describe it. Now then, I'm going to draw another graph first off. Okay, and my graph here is not perfectly correct, but this is the flux that is inside the coil, so the flux that comes from the magnet. Now, with any question in sixth form physics, I always advocate, if you can think of any equation, write it down. So the equation for EMF is minus d phi by dt. So the minus is Lenz's law, which says that the change will oppose, the EMF will oppose the change that's caused it. The d phi by dt is the change in magnetic flux with time. Now, if I just do flux against time, then what I've got here is I've got the flux that is contained inside the coil. Okay? Now, because the flux contained inside the coil is at one point going to be a maximum, that gives us this shape. Okay? Now, this is the graph that we're explaining, okay? And this graph is the change, or is proportional to the change in magnetic flux. So in this first section of the graph, and I'm going to put my line here, we're looking at this half of the graph. So the first half of the graph is this part. So in this part of the graph, we have a negative voltage induced. Okay? In the second part of the graph, we have this positive voltage. And that's this bit. Now, in the middle, we have a zero. Okay? We have zero EMF. And that's because there is no change in the flux. And that corresponds quite clearly to this point here. And there is no change in the flux for a very small amount of time, infinitesimally small, when the entire magnet is halfway through the coil. So anyway, the magnet has been dropped, so it is accelerating, and because it's accelerating, you can say that this part, okay, this distance, is going to take less than this time, okay, than this distance. So it goes in slower than it comes out because it's accelerated. So that roughly explains to you why this bit is shorter than this bit. Now the total flux, okay, this part and this part of these two graphs are equal. Why? Because the flux produced by the magnet and the flux cutting, okay, is a constant. Okay, I'm going to add the n here because obviously it's n d phi by dt, but the number of coils doesn't change, and so you can to some extent disregard it from the shape of the graph. But for completion, just to have everything complete, I'll put it there now. So, I'd like you to look at my rough model answer, and then we'll look at the mark scheme. My answer is this. You can read for yourselves, but I'll read it just in case you can't. The EMF is equal to minus d phi by dt. EMF is proportional to the rate of change of flux linkage. So I'm explaining the equation. As the magnet accelerates, the rate of change of flux increases. So we're saying the magnet is accelerating. So the change of flux, okay, the rate of change is increasing because the flux that's in the magnet is increasing. Okay, the flux that's inside the magnet is increasing, and it's increasing at an increasing rate, which explains this part of the graph. Okay, so here we have some flux entering, okay, but then we have some flux entering at high speed as the magnet accelerates. The areas of the two sections of the graph are equal. Sorry, this is where it's important to proofread your work. The areas of the two sections of the graph, let's just add that in, are equal, as the total flux linkage of each half are constant. So the flux from each half of the magnet is equal. However, as the magnet is moving faster in the positive half, the peak EMF is higher. So that's explaining why this part of the graph is that shape. The direction of the EMF changes from negative to positive due to Lenz's law, stating that the EMF will oppose the change that has caused it. If you didn't have that, you could end up with a graph that looks something like this. Okay, but it doesn't look like that. It looks like that. Okay, that second line that I've just added, or even the graph that we are describing. Why? Because Lenz's law gives us a direction. Okay, so we'll discuss this again in class, but this gives you a little bit of a heads up and should help you in your preparation for the lesson. Okay, now then, I've checked my model answer. It agrees with the mark scheme. Okay, if I put the mark scheme in, then I have, now it's nice and handy at the back here, I've got this first bit, link the magnitude with the induced EMF, okay, and they accept the equation. That's the first part done. As the magnet accelerates, the rate of change of flux increases. Yeah, okay, so as the magnet speed increases as it falls. So I'm talking about it accelerating. Now, I actually do this fourth part here. Okay, this is mark number 4. This was number 2. The areas of the two sections of the graph, as the total flux are equal, as the total flux linkage of each half is constant. And then I go for point 3. However, as the magnet is moving faster in the positive half, the peak EMF is higher. So the direction of the EMF in point 5 changes from negative to positive due to Lenz's law, stating that the EMF will oppose the change that has caused it. Okay. Hopefully this helps. I'm just going to leave you with that. Okay. Have a good evening.